Hello, this is Mr. McMurray, and we are going to talk about gravity. So hopefully everybody appreciates the gravity of the situation because, you need to pass this next quiz, right? Now, gravity is something we're all familiar with, but there's also a lot of things, and we think, oh, we've heard a lot about that in school and stuff, but to be honest, a lot of the time you have not heard a lot of things that you probably needed to, okay? All right, so let's see. First of all, we talk about the theory is, and Sir Isaac Newton was sitting down underneath an apple tree. Now, whether that was really exactly what happened, but probably, to be honest, he was probably sitting underneath the apple tree looking at the moon, okay? And he was at home because there'd been a plague, kind of a pandemic sort of thing. So everybody from Cambridge or Oxford, I forget which, had been sent home. And he was out on the family farm, and it dawned on him that the apple falling out of the tree might be the same force that caused the moon to go around the Earth. That's going around the Earth. Well, Newton thought that maybe the moon isn't falling to the Earth, maybe it's falling around the Earth, just like the apple was falling toward the Earth also. Okay, how could that happen? Well, good question, and we'll get to that. All right, but basically, he came up with the idea of gravity, which is a big deal because up until now, people knew things fell down and they accelerated, like Galileo said, but no one could really explain why or how or what rate that did. Okay, now let's look at some examples real quick and see what we can find out about how things fall. All right, so here we are. First of all, we have this little Nerf rockety thing I got from UNHB, where my daughter used to go to school. All right, now if I take this and I drop it, where's it going to go? Straight down. And what force causes it to go down? Gravity, because gravity pulls things down. We know that, okay? But let's say, what if I were to push it forward and it falls? Okay? It doesn't fall straight down because now, as well as the force acting down, as a force acting this way, and so it goes, this force wants to go forward, this force wants to go down, and it goes kind of in between. So it did kind of a half a parabola, okay, as it's kind of making that arc there. All right? Now, if I make it go faster, you notice it still has a curved path. As soon as it leaves my hand, it starts going down. But now, it's a much longer, flatter curve. Why? Because it's going faster this direction. So it's going faster so much that it doesn't drop. We say it doesn't drop as fast, but technically we know gravity is the same. It's pulling it down just like as if I were to drop it. It's just that it's going so fast this way, so it still falls, but it makes this longer, flatter curve because it's going so fast. Okay? Now, Newton said, hey, maybe the moon is going so fast around the Earth that it curves and falls, but it never hits the Earth because it's going too fast. And it goes around the curve of the Earth before it hits the Earth. And so instead of falling to the ground, like an apple or something like that, maybe if it goes fast enough, then it can circle around the Earth, okay? And so it's always falling, but it's falling around the Earth because it's going so fast, okay? Now, how fast does it have to go before it can fall around the Earth? We'll get to that in a little bit, all right? But first, let's talk about the law of universal gravitation. This is the law that Newton came up with, okay? And basically, he said, the law of the force of gravity, Fg, force for F, F for force, little g, so it's force of gravity, is equal to, or he didn't know exactly what it could equal to, he being a precise mathematician, but it was proportional to. The little squiggly lines mean not equal, but proportional to. Okay, it's proportional to two things, just like we did speed was proportional to distance over time. Okay, same thing. He said it's proportional to the mass of the two objects. Okay, and so basically, if you have the mass of two objects, there's always an attraction between any two objects. If I'm walking down the street, there's an attraction between me and the cars parked on the side, me and the sidewalk, me and the buildings, me and the people walking next to me. There's always an attraction there. Why? Because Newton said that any two masses will be attracted to each other. And he said the bigger the mass, these are on the top of the fraction, this is going to be a fraction here, these are on top of the fraction. So the bigger the masses of one or both objects, then the more gravity there's going to be. So they're going to be directly proportional to how big the objects are. Okay? Now, We'll talk more about this in a little bit. But gravity is a weak force, okay? It is not very strong. Someone says, what? You jump off a building and see how strong it is. But it's relatively weak. The only gravity we feel, do we feel the cars and the houses and the people walking next to us, or a piece of paper in my hand? Do I feel the attraction to it? No. Why? Because it's a very, very weak force. The only gravitational attraction that I feel is between me and the Earth. And that's not because of I'm so big. That's because of the mass of the Earth is so humongous. So I actually feel it. Okay? If I went to the moon, which is only 1/6 as big, it would have a smaller mass. I would still have the same mass number one. It would have mass number two. It would be 1/6 as much. And so the force of gravity would be 1/6 as much. So basically, he said it's directly proportional to the mass of the two objects. Okay? If one or both of them are large, that's going to increase the force of gravity between them. All right. And so we call the force of gravity weight. And that's why if there's more of me, I have more mass, say than when I was a baby, then now I have a greater force of gravity pulling on me. You and I and everybody in the room does not have the same force of gravity because we all have different masses. Okay. It's pretty close, but our weight or the force of gravity on us is different for each one of us. Okay. So force of gravity is not the same for everything. All right. It depends on their mass. All right. Now, he said it's inversely proportional, or goes in the opposite direction. You increase the mass, you increase the force of gravity, but it goes the opposite if the distance between the two objects squared. Okay? So if the two objects are farther apart, they will feel less gravity. Okay? So if the distance is, and it's distance squared, so say you get twice as far, that would be 2D, twice the distance squared, that would actually be 4D squared. So because it's squared, it's going to be a great bigger difference, okay? It's going to be the squared of how numbered. If it's 3 times as far apart, that means there's going to be 1/9 as much gravity, okay? If they're twice as far apart, it's only going to be 1/4 as much gravity, okay? So the bigger the distance gets, the less gravity you have, and not only that, but it's inversely squared, okay? Inversely proportional, and it is squared. So distance has a very big difference on that, okay? Now, clarify something though. Say we're talking about the Earth, all right? And you're here, which obviously even Godzilla is not that big compared to the Earth, but it's not in proportion, but you get the idea, okay? Technically, it's not just how close you are to the Earth, because you're sitting on the Earth, right? It's actually the center of your mass, which is somewhere around your belly button, and the center of the Earth's mass. That's the distance we're talking about. And I believe it's 6,371 kilometers. We're just going to call it 4,000 miles, okay? It's actually, 3,959. We're going to forget about those 41 miles. Heck, what's another 41 miles after you've gone almost 4,000 anyhow? So we're just going to call it 4,000 miles. That's the distance that's squared here. Okay? So our distance is 4,000 squared. Okay? So that's a pretty big number. All right? It's only because the Earth is so humongous that we still feel the force of gravity. All right? So if we wanted to be twice as far, we would have to get another 4,000 miles above the Earth. And then we would feel 1/4 the gravity. Okay? But just for the record, airplanes and Mount Everest and so forth are only about 5 miles. Not even close, anywhere near to that. So if we're anywhere on Earth or even flying above Earth in an airplane or something like that, basically our gravity is still the same. Why? Because the distance is not that much different. 4,000 and 4,005 miles, there's not much difference, okay? You can calculate it. I think I did that in the quiz or in the other lectures. Basically, if I weigh 200 pounds, I might be 199.5 or 0.4. So I might lose half a pound if I'm up in an airplane, but not enough to really make it worth a big deal, or top of Mount Everest or something like that, okay, if I was 5 miles above the surface. So basically, as the distance goes, it really decreases the force of gravity. So mass is directly proportional to the force of gravity. If mass is increased, then the force of gravity increases by the same amount. it's inversely proportional, or you do the opposite. If you increase the distance, you decrease the force of gravity. And not only is it inverse, but it's squared. So if it's 4 times as far away, say this was a 4 here, then this would be 1/16 as much of the force of gravity. Okay, so distance really, it diminishes pretty fast with distance. All right, but keep in mind the distance we'd have to be above the Earth is, to double it would be 4,000. So yeah, you got to go quite a ways in that case of the Earth because it's so big. All right. Now, this decreasing because of distance is called the inverse square law. Okay, because one, we say it's inverse. It's on the bottom of the fraction. That means if this number gets bigger, this force gets smaller. That's the inverse part. And it's squared, so that means it gets even smaller. All right. Let me look at a quick picture if I can, and we'll try that. All right. It's kind of like, see if I can get that picture to come up. There we go. Okay, it's kind of like this picture here. If you were spraying paint and say you were 1 foot away, there'd be a certain amount of spray paint, okay? Now, if you ever spray painted, you know it's hard because you either get too much paint and it runs, or you don't get enough and it just barely coats it and you have to keep going over it and over it, okay? Here's part of the reason why. Well, because as you get farther away from it, say we get 2 feet away, okay, over here, okay, the distance has been increased by 2. We've doubled the distance, but we get only the same amount of paint spread out over 4 times as much area because the distance has been squared. If you go 3 times as far, 3 feet away, now the same amount of paint is spread over 9 units of area, and you get the idea. Okay, it continues. Now, same thing with light. The same thing happens as light. As you get farther away from the light, it's the same amount of light coming off. It's spread over a bigger and bigger area as it gets farther away from the light, and it gets dimmer and dimmer. Same thing, the inverse square law. Well, we can't see gravity, but gravity does the same thing. As you get farther and farther away from Earth, then you feel less and less gravity. All right, but like I said, it's 4,000 miles to the center. So it takes a long ways to get that far away before you really notice it, but it would eventually happen. All right. So if you were 4,000 miles up here in outer space, then you would weigh 1/4 of what you do here. I weigh 200. I would weigh about 50. Okay. But you have to get 4,000 miles above the surface before you feel that. Okay. Now, that brings us to an important question, though. How far do I have to get to escape the Earth's gravity? Well, that's a good question, but the answer is you never escape the Earth's gravity or the sun's gravity or any other object in the universe, okay? Or your notebook or your computer or whatever, or this foam rocket. Why? Because as I get farther away, this number gets bigger and bigger and bigger, and the force of gravity gets smaller and smaller and smaller, but it's never equal to 0, okay? Because we still have mass in the object, and this number just gets bigger and bigger and bigger. It just gets smaller and smaller and smaller. So eventually, you get so far away from the Earth, the force of the Earth's gravity on you is so small you don't feel it. Just like right now, you don't say, oh, I feel the sun pulling me toward the sun. But technically it is, okay? But you don't have enough mass for it to affect you. Now the Earth does. Between the Earth, multiply the Earth's mass times the sun's mass, and even though there's a very great distance between us and the sun, it's still enough to keep the Earth spinning around the sun. Okay? So, the same thing, we're feeling the sun's gravitational pull, but we're so small and the distance is so much, we don't feel that force on it. Remember, gravity is a weak force only felt by very large objects, usually like planets and suns and things like that. All right? But you never get away from the Earth's gravity. You just get to the point where it's so small, we say you have 0 gravity. Technically, what we're saying is you have so little gravity you are not aware of it. Okay? But technically, there's never 0 gravity. All right? Now, eventually, what they do, they want to try to measure gravity. Well, the problem is it's very difficult to measure gravity because the Earth's gravity is so overwhelming. So what they did, if I can get this one to pop up. There we go. All right. They took a really precise balance, okay, and they put a metal ball on it. That'd be mass number 1, and they balanced it. Okay, now they put it in a room kind of all by itself. They got outside the room. In fact, originally they looked through a keyhole. They were afraid to even get their bodies in the room. Okay, then they rolled this really big ball up next to it. Okay, well, any two objects with a large mass are going to attract each other. So that pulled this ball a little farther down, and they had to add a little bit of extra weight or force over here to balance it. Okay, and they could actually calculate how much force of gravity. You got the mass of the two balls, all right, and the distance. You knew how far it was between the center of the two balls right here. This is from here to the center of this one, okay, and they could calculate an exact formula now, okay. Instead of just saying force is proportional to mass 1 times mass 2 over distance squared, they can now say it's equal to that times big G. Some stuff, big G. What's the heck with that? Okay, well, it has to do with gravity, of course. It's called the gravitational constant. Okay, and it's kind of like pi. Pi is a constant that converts the you can use to convert the radius to the circumference and so forth. And it's consistent. No matter how big the circle is, it's always 3.14 times the radius gives you the circumference, and that's just the way it is. Okay, I think I got that right, but I'm not a geometry person. Okay, all right. Well, same thing here. Not only do you multiply the mass times the mass divided by the distance, but you got to adjust it to get to force, get to units of force. You have to multiply it by g. Okay. Now I don't want to spend a whole lot of time on g, but here's the deal. G, once they calculated it, was 6 point what? Let me get to 6.67 times 10 to the negative 11. Okay, now there's some units. We're not going to worry about that. Basically, it's newtons, and it has meters squared, and it has kilograms or mass squared to make those units work out. But don't worry about the units. Okay. The point is, this is a very small number. This is 0.0234567 667. Okay, it's a really, really small number. Okay, so it's not much. Okay, so gravity is basically a fairly this was done in the 1970s, about 100 years after Newton, and we can see that actual force is exponent. Instead of multiplying it by 3.14 or something, we multiply this very small number. Even if you have pretty big masses and you divide by the distance, you take that number and you multiply it by this, you're going to get a really small number. And so that's why we say gravity is a really weak force. Unless you got really big objects like planets and suns and stuff like that, we don't even notice it most of the time. Okay. Now, one other thing, a little thing. Once they figured out the G, they could plug that in here. They knew the distance to the center of the Earth, between us and the center of the Earth. They put our mass here, the thing there. They know that your weight, that's the force of gravity. And they could solve this for the mass of the Earth, which was a big deal back then in 1700s. And they found out, just for the record, the Earth is 6 times 10 to the 24th kilograms. That's 6 times 24 zeros after it. Okay, it's big. Okay, it's kind of neat that they could do it as early as in the 1700s, and that was really big, and people were impressed. And I'm sure they had parades and all that kind of stuff. Okay, now let's keep something in mind here. Let's talk about something when things fall, and talk about that for a second. But let me get ready. See how good this works. I may have to describe what happens after it happens. But here we go. We have this. Don't worry about this. This is a little handle. This is like a cannon. Okay. And we're going to put one steel ball bearing in there. Ooh, shooting a cannon and ball bearing out of cannon. That sounds promising. Okay. And then we're going to put this one on here. It has a hole on it. Sorry. And it fits right there. And so here's what happens. We're going to have a little trigger here. When I pull this, this will go that way, which means it will pull out of the ball and leave the ball, let it fall straight down because inertia. It pulls out, the ball falls. All right. And it will hit at the same time. As the plunger goes this way, it will hit the ball inside there and shoot it out. Okay. Well, I wanted to try to see, I don't know if you'll be able to see it on the video or not, but we'll try it. I want to see which ball hits the ground first. In other words, the ball that just falls straight down or the ball that shoots out. Okay. So let's see if we can do this. All right. Now, it may have been better to listen for the sound, okay? But basically, what you should have heard is that the two balls hit at almost exactly the same time. Someone says, well, I couldn't see the ball. Sorry, go back and put it in slow motion or something, frame by frame. But you have to take my word for that. But they should hit at the same time. Why? Because there's a downward force on them, which is gravity. They both weigh, have the same mass. So mass number one, and the Earth is mass number two. That's the same for both balls. So basically, they will fall at the same rate. In other words, going forward does not change how fast gravity makes something fall down. That's an important concept. We'll come back to that. I'm going to launch a little rocket here off our rocket launcher. I have a red thing here. I'm not sure how well you'll see this once again on the TV screen, but we'll probably try to let you see the most possible. All right, here we go. All right, now if we have this as a projectile, projectile is anything that either falls or gets shot, thrown in the air. Okay, this is going to be our red rocket here. If I pull it down here and I launch it, it makes a parabola, okay? All right, well, let's talk about that for just a second. All right, so let's talk about projectile real quick. Projectile is a stone, cannonball, anything that is projected or tossed either into the air or down and continues in motion. Okay, that's just a projectile. It's been projected or thrown or tossed. Okay, now if we live in a world without air resistance for a second, okay, say we were with a vacuum, okay, but we do have gravity. All right, if we throw a ball, it will make this nice thing like this, okay? Or just like the rocket I just did. It will do this. Now, when I let go right here, it has a certain force going forward, and it has a certain force going up, okay? And those two vectors add together give it this path, okay? And anywhere you go along this, it's going to have a combination of those. But as it goes up higher, all right, say we do for the same length of time, 1 second, all right? If there's no air resistance, there's nothing pushing this way, so the forward arrow right here and right here are going to have the same amount of, but you notice that this one is getting shorter. The height is getting shorter. Why? Because gravity is decelerating it or pushing it, force against it, and it's a greater force than the ball has. So it's getting less and less. And finally, here at the top, it just has forward, but it doesn't have any going up at all. Okay, it's at the zero at that point. Okay, so we kind of draw it would be just going forward, and it would be the same amount. Okay, but it would just be going straight forward. There's no up or down thing of it. Now, as it comes down, gravity's still acting on it, so it's going to start accelerating. So now it's going to have a down component, but it's still going to have the same forward component, and so forth all the way down. Okay, and so it's going to have the same forward concept, but the downward is accelerating because it's getting more and more. And so there's two components to the force that make it go forward. And they're two separate forces, okay? Gravity does not affect how far forward it goes each time. All right. Now, in real life, usually we have air resistance, okay? So what actually happens is you get a ball that, say, a quarterback throws here. And it goes left. Why? Because not only does, as it goes up, does the upward force get less because of gravity. Sorry, I did that. Okay, but you are also getting where air resistance is pushing back, so it's not going as far forward every second. Okay, and so it's decreasing, and it doesn't end up going quite as far. Now, my drawing was not probably 100% accurate, but pretty close. There we go. Okay, and so in real life, with air resistance, you get this. Okay, if you have a greater wind, you have more air resistance, and you get even a less slower one like this. If you're throwing a pass in football, you've got to take those kind of things into consideration because you're throwing a projectile. All right, and as soon as it leaves your hand, gravity is going to be slowing it down. If you want to throw the ball straight to someone, you can't throw it straight to them because as soon as it leaves your hand, gravity starts to pull it down. Okay, and so it's going to hit the ground if it's a very far pass. So usually short passes can be straight. Okay, and even then, we have to throw them up a little bit so that gravity slows it down and then it comes back down and hits where we want it to, equal like the numbers of the person catching it. Okay, because as soon as it lets go of the quarterback's hand, it's going to go down. Even when he throws those straight hard passes, that's why they have to be short because he's got to get there. It's got to be really fast, and it gets there. So by the time it gets there, it's only fallen a little bit. It's only had a quarter of a second or something to fall, and so it hasn't had time to fall very much. Otherwise, he would miss his target. Okay, and so anyhow, now the path of this. First of all, let's get these two things. The path of the projectile, okay, is called a trajectory. Okay, when we talk about the rocket's trajectory, we're just saying what's the path of the rocket. So the trajectory is the path, okay, and the shape of the path, this one is a parabola. All right, so a parabola is the shape. I can't spell S-H-A-P-E. Thank you. The shape, all right, of the path is a parabola, but the path of it is called the trajectory of the projectile. Okay, so that's just some things about projectiles. Now, we said that generally they're going to make this kind of a path, all right? If we were to shoot it straight out, well, let's try that and see what would happen with our rocket launcher here real quick. What's good at having a rocket launcher if we don't use it, right? I'm going to shoot a projectile straight out from the rocket launcher. There we go. And if I do that, I cannot make it. All right, I think we're working again. I cannot make it go in a straight line. Why? Because I can't make it go fast enough. Gravity starts making it fall so fast that it can't stay in the air long enough to get over to the door. Okay, sorry, I think I may have been not a real good picture there either of the rocket launch, but hey. And so I can't. Now, if I had a bullet on the other hand, if I had a rifle shooting a bullet, I could shoot the door and I could hit it pretty much right where it is. Why? Because it's going so fast, it doesn't have time to fall very much, even though gravity's still going to make it fall. Okay? Kind of like the steel balls we did earlier. If I had a bullet and I drop it, and I have a bullet and I shoot it down the range, which one's going to hit the ground first? They're going to hit the ground at exactly the same time, assuming I shoot it perfectly straight. Now, if I shoot it up, then yes, it's going to go up. Gravity's going to have to slow it down and bring it back down, make that parabola. But if I shoot straight, gravity's going to start bringing it down, and they will hit the ground at the same time. Okay? And so it doesn't matter whether it's going forward or not. Gravity's still going to bring it down at the same rate. Okay? And if I'm shooting far enough with a gun, I have to shoot above, say I'm shooting across the canyon at a deer, I'm going to shoot above it so that it has time to move that parabola and come back down and hit the deer. Okay, and the farther away the shot is, the more I'm going to have to try to do that. And of course, you also have more air resistance, and you have wind and stuff like that as well, so it gets more complicated unless you're a really good sniper or something like that. Okay, so let's pause for a second, and we'll be back. All right, so now let's say we're trying to make a projectile that will go around the Earth. We don't want it to ever hit the ground like that bullet we were talking about. Okay, well, it turns out that on the average, now if this was the Earth perfectly flat, obviously there's mountains and now we've got skyscrapers and things in the way and things like that. But if it, on the average, for every 8 kilometers or 8,000 meters, 8 kilometers is 8,000 meters, for every 8,000 meters, the Earth curves. I know some of you thought it was flat, but no, it's not. It is curved. Okay, and it curves. And it turns out that it drops about 5 meters. If you're sitting right here and going straight out, by the time you got 8,000 meters or 8 kilometers, which is about 4 to 5 miles, it's going to drop 5 meters, okay? That's on the average. All right, so here's the deal. If you could make something go 8,000 meters per second, okay, that means in 1 second it would fall 5 meters. I'm sorry, we didn't do this, but if you drop something based on the 10 meters per second squared, that means that every force of gravity, the acceleration of gravity, g, remember, is 10. Yeah. Whew, okay, try to get that. All right, the acceleration of gravity we know is 9.8 Newton meters, or 10, basically. We'll say 10. All right, well, it turns out then that means that in 1 second, it will have dropped 5 meters. So if you can make something go 8 kilometers in 1 second, then it will drop and it will stay the same distance it was above the surface here. Okay, now, How fast is that? Well, that's about 18,000 miles per hour, okay? So, no, we're probably not going to get out of my car or your car and go out and go that fast, okay? Even jets and things like that aren't usually going that much. But if we want something to be a satellite, it has to hit that much speed so that it does not drop more back toward the Earth. So if you're shooting around the Earth at 8 kilometers per second, all right, or 8,000 meters per second, and Earth is pulling you, you could perfectly go around the Earth, because even though you're constantly falling, you're going fast, but you're going so fast, you're not falling very much compared to the surface, okay? Because you're going so fast, you don't have time, and you're not falling. You're falling at the same rate that the Earth curves. You would just stay completely around the surface, okay, which would be kind of cool. Okay, someone says, "Oh, so we could do this." Okay, we could have the girl. She throws this rock. It's 8,000 meters per second. It comes around and bonks her in the head. Theoretically, yes, but there's a problem, because on the Earth's surface you have atmosphere, and the atmosphere is going to create friction, and the faster you move, the more air resistance and therefore friction you have. Okay, so guess what's going to happen to this rock? If it were going that fast, it would burn up, okay, just like a meteorite entering the Earth's atmosphere. As it accelerates through the atmosphere, it burns up. Well, that's exactly what would happen here. All right, so here's the deal. If we want a satellite to go around the Earth, we have to have it far above the Earth's surface, okay? And sometimes people think, oh, that's because it gets away from the Earth's gravity. That is incorrect, okay? The International Space Station is only about 250 miles above the surface, okay? Remember, the distance from the center of the Earth to the edge is 4,000. While going up another 248 miles, 250 miles, it might reduce your pull of gravity a little bit, but you're not even doubling it, which makes it 1/4. So you're probably not going to weigh. If I weigh 200, I might be down to 175 or so, but obviously not weightless. 175 people still don't float around in open space, right? So what happens? Well, basically, they are going so fast, okay, that even though gravity is pulling them down to the Earth, they're going so fast that they're staying the same distance away from the Earth. And so we say they're falling around the Earth as long as they can maintain that speed, okay? And so, but the reason they have to go, and all satellites go at least 150 miles above the surface, why? Because they have to get above the Earth's atmosphere. The Earth's atmosphere would burn them up. The space shuttle had to have the special tiles. Why? Not so much when it's actually in orbit, because it's above the Earth's atmosphere, but once it comes back down to land in the Earth's atmosphere, that's when it needed the protection. When the one that blew up, that's what happened. They had trouble with the tiles coming back in. It overheated and it exploded. Okay, so we have to send satellites a certain distance from the Earth, not to escape the Earth's gravity, not because there's that much less gravity up there, but because it gets them out of the atmosphere, which keeps them from burning up. Now, if you're inside that space shuttle or the International Space Station, as you're going around, you're falling, gravity's pulling you down, but you never hit the floor of the space station, basically, and we have what we call weightlessness. Okay, weightlessness is a little different than no gravity. All right, to give an example that we could use in every day, let me blow this up a little bit. Okay. So, say you are on an elevator. We were on one the other day. It had glass all around it. Kind of freaked us out a little bit, but it was kind of fun in a good way. All right. And here's the deal. All right. Say you're in the elevator and you're sitting on some scales. All right. I say you because this is not me. I'm much better looking than this. All right, but you get the idea. All right. So I'm sitting on this. I'm sitting on the scales. If I'm sitting on the scales, the elevator stopped. It just shows that I weigh 200 pounds or 940 newtons, whatever. But anyhow, all right, 200 pounds. All right. But if I go up, if it goes up, not only am I pushing down the scales, now the floor pushes up against me, and my inertia, I sit there and it pushes up against me, so I get extra force. And so it might say, when it goes up, it might say that I weigh 205 or 10 pounds. Okay? Do I really weigh more? No. But now I have the force of the floor pushing up, and so it appears that I weigh more. Okay? It appears that I have, we call it your apparent weight, because it looks like you've increased your apparent weight. Okay? Now, if I go down, you've always seen that one. Whew, feels like the bottom dropped out, right? So since the bottom goes down and my inertia holds me here for a minute, I don't push as hard down on the scales And so it might say that, oh, I only weigh 190 pounds. Did I lose weight? No, it's just that my full weight's not pushing down on it. All right. Now, normally we're attached by a cable that's letting me go down or pull me up. If we break this cable, now the only thing that's pulling me down is gravity. Okay, it's pulling the bottom of the floor down, and it's pulling me down at the same rate. Okay, and guess what? Since we're both falling at the same rate, the scales read 0 because I'm not pushing down the scales. That's all weight is how much I push down on the scales. Well, that's kind of what the space shuttle is doing, or the International Space Station. They're going around so fast, but they are falling around the Earth, but they're falling enough that we never catch up with it, so we feel weightlessness. Okay, that was a way to test this. I mean, they have tried putting the astronauts in swimming pools with weights and stuff, so they feel kind of weightless. But we need to find a better way to do this. So they had an airplane, and it would do basically what this would do. It would dive down so fast that they couldn't fall and hit the bottom, so they had the feeling of weightlessness. But you can't run into the Earth with this airplane, so you had to level out and come back up and then go back down. And needless to say, that could be a little unsettling to the gastrointestinal stomach tract. And so they call it the vomit comet. Why? Because it made most people really sick. But it was a chance for the astronauts to feel this weightlessness that you would feel. Not zero gravity. There's not any gravity. The gravity is there, but they're never coming in contact with the surface because the surface is dropping, okay, around the Earth, and so they never come in contact with it, and therefore they don't feel gravity. All right, so we call that weightlessness. But notice that's not the same as not having any gravity. All right, now let's talk a little bit about the period. If say this is the Earth, we're going to draw it fairly small, okay, because we're going to be up here above it going around, okay. So I know this may not be to scale, but that's okay. So let's say we have and this one is about, I believe, we'll say 18,000 miles above the Earth. Okay, so this one's 18,000 miles above the Earth. Okay, this would be like, as it circles the Earth, every time it goes around is an orbit, and the length of time that it takes is a period. Okay, a period is something that repeats over and over again. Okay, and so one lap, another lap, you just keep repeating, and it takes the same length of time. But to stay that same distance, okay, it has to go at a certain speed. All right, let's compare that to say one that was out here at a farther distance. Let's just say twice the distance, although probably not the way I drew it, but you get the idea. Okay, say it's 36 out here. Okay, now, first of all, which one is going to take more time to get around? Well, first of all, this one is shorter, this one is longer. So you think, well, this one's going to be a shorter period. All right, and that's true. But not only that, the other thing is, which one is going to feel more gravity? Okay, obviously, now this is 18,000 miles, give or take 18,000 miles, give or take a little bit, okay? And we said it was 4,000, so this is 4 times above the Earth, okay? So you're actually going to feel some change in the gravity here. But this one's going to feel more gravity because it's a closer distance. Remember the formula, if the distance on bottom, if it's smaller, which this distance is smaller, this distance is going to be farther, okay? Then they're going to feel less gravity. So since this has less, and since this one's closer, it's going to feel more gravity. Sorry, so this one's closer, it's going to feel more gravity. And so it's going to have to go faster to keep from being pulled down to the Earth. Just like that bullet's got to go fast so it doesn't get pulled down by gravity. So this one has got a smaller distance, okay, to travel in the first place. The circle is smaller to orbit the Earth, and it has more gravity, so it has to go faster to do that. So it's going to have a very short period. Now, as you get farther away, gravity is less, so you don't have to go as fast to keep from being pulled into the Earth. So you can go slower, and you have a longer circle to make to orbit the Earth at the farther distance. And so both of those are going to result in your having a long period. Okay, and that just kind of makes sense, and that has to do with gravity. Now, the extreme of this would be the moon, which would be probably off the board if we did this to scale, but the moon over here, okay, and the moon is 238,000 miles away, okay, and its period of, well, for example, the International Space Station, when it does it, it actually circles the Earth, I believe, every 90 minutes, okay, in an hour and a half. It makes the whole circle around it all the way, okay? The moon, on the other hand, is so far away and it doesn't need as much speed, so it moves relatively slow. It takes it 29 or 27.3 days, okay? And it's only going 1.02 kilometers per second, okay? A lot lower than that 8 kilometers per second that you have to do to stay from crashing into the Earth at the Earth's surface because it's so far away that the pull of gravity is so low that it can go at a very slow speed and still stay above the Earth and not crash into the Earth. All right. All right. Now, some planets are what we call geosynchronous. Geo means Earth, synchronous means synchronized. All right. And basically, they go above the Earth, and they always say, here's your little house. They follow your house around the Earth as it rotates. Okay. And so they keep up with your speed. This is important. If you have satellite TV, you don't want a satellite that, circles every 90 minutes because that means for at least 45 of it, it's going to be on the other side of the Earth and you're not getting any signal. Okay? And you can still have trouble with clouds and stuff interfering with the signal, but you want a satellite that stays above you so that you constantly get satellites and you can watch TV at any time of the day or night, right? And so those are geosynchronous orbits, okay? And technically they have to be 5.5 radii. That would be that 24,000, okay? 5.5 radii of the Earth away, okay? So you can multiply that by 4,000. I think that's going to be about 22,000 miles above it. And that way they can stay just right above the Earth. They rotate at the same speed. They'll have a velocity of 3.7 kilometers per second, and that will keep them right above the same place at Earth. If they go at that speed, that distance, then that will keep them right above where you can get a constant signal. Okay. Now we said if a satellite leaves Earth, you will have a elliptical orbit. Okay, I'm not going to talk about a lot about that because I don't have a lot to say, but it will have like this. Okay. Now, where is gravity the strongest? Well, when you're closest. Okay, the force is going to be stronger. And since the force is pulling you, it's going to speed up here. Then as it goes away, it's going to lose kinetic energy. All right, so it's going to lose or decrease kinetic energy. And it's going to increase potential energy because it's getting farther away. Okay, as it gets the farthest place out here, it can't quite pull away, doesn't have enough speed to pull away, okay, because it's between 8 and 11.2 kilometers per second. It can't pull away from the Earth, so it gets pulled back. But as it comes, so up here it's all PE, but it's very low kinetic energy. Then as it comes back here, it loses potential energy and it gains kinetic energy because it's getting pulled. The force of gravity is getting stronger, and so it gets in this what we call an elliptical orbit. Okay, now if you reach 11.2 kilometers per second or higher, we say that is the escape speed or escape velocity. Okay, and that's what you need to get away from Earth. From the surface, you have to get up to a speed of over 11.2 kilometers per second. This is why all the big rockets have the big fuel tanks on them. This is the hard part, getting the rocket to escape velocity so it can get away from Earth. Once it gets away from Earth, where the gravity is not enough to count, then basically it doesn't take much to keep it going because of inertia. And so it's all about escaping the Earth. Now, this is why also, though, in the future, they're thinking if they go to Mars, somewhere like that, if they can get a launch ship up into, say, the International Space Station, put it together there, it's far enough up that there'd be less gravity. It wouldn't take as much to escape into outer space. And so that's kind of one of those kind of things. But from the Earth's gravity, the force of Earth's gravity, you need 11.2 kilometers per second to escape. Okay, if you're on these farther out of these satellites, you could speed up and would find it easier to escape. Why? Because you're farther from Earth and you don't have the same amount of gravity that you need to escape. All right, but that is it. Now keep in mind that's when we say escape the Earth's gravity, we mean you can't ever escape it. There is no escape from the Earth's gravity, and it only gets weaker and weaker and weaker. Okay, but technically there's always some amount of gravity acting on you. All right, last demo. We have this. This is just a water on the thing, and we've kind of done something like this before. See if I can do this without breaking it. Anything? I don't know. I may have to scoot back a little. All right. So if I swing this, then it says, well, why does the water, if it goes overhead, does not spill out? Well, there's several things. We talked about inertia before, but also keep in mind when it's right above my head, there is a force of gravity acting on it, pulling it down. But when I'm throwing it, the acceleration of it moving up there has to be strong enough to counteract the acceleration of gravity so that it does not come down. Okay, and that's why I have to swing it at a certain speed. If I go very slow, then there's not going to be enough force of gravity to overcome. There's not going to be enough force pushing it out or away from me, and gravity is going to overrule it, and it's going to come down in a parabola or straight down on my head, probably with no luck. All right, and I would demonstrate that, but there has to be a limit on what you will do for science. All right, so anyhow, don't forget. Second article is coming up, I believe, for the people watching this, it would be the 27th, but check your schedule. That first article summary is, don't let it creep up on you. It is coming. And, of course, you got your questions in by Saturday and your quiz in by Monday, or in the case of dual credit, on Tuesday. All right? Second test is coming up, too. One more chapter, and then we will take that as well. Have a great week.